let's review a little bit of what we learned in differential calculus. Let's say we have some function s that it gives us as a function of time the position of a particle in one dimension. If we were to take the derivative with respect to time, so if we were to take the derivative with respect to time of this function s, what are we going to get? Well, we're going to get ds dt, or the rate at which position changes with respect to time. And what's another word for that? The rate at which position changes with respect to time. Well, that's just velocity. So that we could write as velocity as a function of time. Now, what if we were to take the derivative of that with respect to time? So we could either view this as the second derivative. We're taking the derivative not once, but twice of our position function. Or you could say that we're taking the derivative with respect to time of our velocity function. Well, this is going to be, we can write this as dv dt, the rate at which velocity is changing with respect to time. And what's another word for that? Well, that's also called acceleration. This is going to be our acceleration as a function of time. So you start with the position function, take its the position as a function of time, take its derivative with respect to time, you get velocity. Take that derivative with respect to time, you get acceleration. Well, you could go the other way around. If you started with acceleration, and you were to take the antiderivative, of it, an antiderivative of it is going to be, actually, let me just write it this way. So an antiderivative, I'll just use the integral symbol to show that I'm taking the antiderivative, is going to be the integral of the antiderivative of a of t. And this is going to give you some expression with a plus c. And we could say, well, that's a general form of our velocity function. This is going to be equal to our velocity function. And to find the particular velocity function, we would have to know what the velocity is at a particular time, and then we could solve for our c. But then if we're able to do that, and we were to take the antiderivative again, then now we're taking the antiderivative of our velocity function, which would give us some expression as a function of t and then some other constant. And if we could solve for that constant, then we know what the position is going to be. The position is a function of time. Just like this, we would have some plus c here, but if we know our position at a given time, we could solve for that c. So now that we've reviewed it a little bit, but we've rewritten it in, I guess you could say, thinking of it not just from the differential point of view or for the derivative point of view, but thinking of it from the antiderivative point of view, let's see if we can solve an interesting problem. Let's say that we know that the acceleration of a particle as a function of time is equal to 1. So it's always accelerating at 1 unit per, and I'm not giving you time. Let's just say that we're thinking in terms of meters and seconds. So this is 1 meter per second, 1 meter per second squared right over here. That's our acceleration as a function of time. And let's say we don't know the velocity expressions, but we know the velocity at a particular time. And we don't know the position expressions, but we know the position at a particular time. So let's say we know that the velocity at time 3, let's say 3 seconds, is negative 3 meters per second. And actually, I'm going to write the units here just to make it a little bit. So this is meters per second squared. That's going to be our unit for acceleration. This is our unit for velocity. And let's say that we know, let's say that we know that the position at time 2, at 2 seconds, is equal to negative 10 meters. So if we're thinking in one dimension, if this is moving along the number line, it's 10 to the left of the origin. So given this information right over here and everything that I wrote up here, can we figure out the actual expressions for velocity as a function of time? So not just velocity at time 3, but velocity generally as a function of time, and position as a function of time. And I encourage you to pause this video right now and try to figure it out on your own. So let's just work through this. We know that velocity as a function of time is going to be the antiderivative of our acceleration as a function of time. Our acceleration is just 1. So this is going to be, the antiderivative of this right over here is going to be t, and then we can't forget our constant, plus c. And now we can solve for c because we know v of 3 is negative 3. So let's just write that down. So v of 3 is going to be equal to 3 plus c. So every place where I saw the t, or every place where I have the t, I replace it with this 3 right over here. Actually, let me make it a little bit clearer. So v of 3 is equal to 3 plus c. And they tell us that that's equal to negative 3. So that is equal to negative 3. So what's c going to be? So if we just look at this part of the equation, or just this equation right over here, if you subtract 3 from both sides, you get c is equal to negative 6. And so now we know the exact expression that defines velocity as a function of time. V of t is equal to t plus negative 6, or t minus 6. And we can verify that. The derivative of this with respect to time is just 1. And when time is equal to 3 minus 6 is indeed negative 3. So we've been able to figure out velocity as a function of time. So now let's do a similar thing to figure out position as a function of time. We know that position is going to be an antiderivative of the velocity function. So let's write that down. So position as a function of time is going to be equal to the antiderivative of v of t dt, which is equal to the antiderivative of t minus 6 dt, which is equal to, well, the antiderivative of t is t squared over 2. So t squared over 2, we've seen that before. And the antiderivative of negative 6 is negative 6t. And of course, we can't forget our constant. So plus c. So this is what s of t is equal to. S of t is equal to all of this business right over here. And now we can try to solve for our constant. And we do that using this information right over here. At 2 seconds, our position is negative 10 meters. So s of 2, or I could just write it this way. Well, let me write it this way. S of 2 at 2 seconds is going to be equal to 2 squared over 2. That is, let's see, that's 4 over 2. That's going to be 2 minus 6 times 2. So minus 12 plus c is equal to negative 10. Is equal to negative 10. So let's see, we get 2 minus 12 is negative 10 plus c is equal to negative 10. So you add 10 to both sides, you get c in this case is equal to 0. So we figured out what our position function is as well. The c right over here is just going to be 0. So our position as a function of time is equal to t squared over 2 minus 6t. And you can verify. When t is equal to 2, 2 squared over 2 is 2, minus 12 is negative 10. You take the derivative here, you get t minus 6. And you can see, and we already verified, that v of 3 is negative 3. And you take the derivative here, you get a of t just like that. Anyway, hopefully you found this enjoyable.